Okay, hello everyone, and welcome to Unit 9, artificial spiking neural networks. All right. So this is our last content unit of the semester. We're going to have exam 2 after. So this is okay. We're going to have exam 2 the week after this, then project presentations on the last day of class before Thanksgiving, and on the scheduled final time, and that will be it, right? So we're drawing toward the end. Spiking neural networks, I think, barely edged out autoencoders. I can't remember that looking at the site right now. And I will admit that I was happy to see it win legitimately. I was willing to put my finger on the scale a little bit because I think spiking neural nets are very cool. I will also say to you that I originally wanted to write a lot of code for this one that we could kind of experiment with, but I sort of quickly figured out that was going to take way too much discussion. If we wanted to get to how spikes propagate between neurons in the code that I was writing, we were going to have to talk about the observer pattern, and then if we wanted to do like the dopamine reward stuff, the code was going to end up being very complicated, and there just was no way to get through all of that in about an hour. So what this has wound up being is a fairly high-level overview, right? We're not really going to be looking at a lot of code for this one. Although a lot of this code isn't that difficult to write and get through if you have a little more than an hour to talk about it. But yeah, so we're gonna have kind of a high-level overview here. So we've been talking a lot about artificial neural networks, right? ANNs, feed-forward, fully connected artificial neural networks. The name might be a little bit okay, sorry. So these often sort of borrow ideas and inspiration from biology, right? And a good example is the convolutional neural network, right? Which was sort of inspired by studies of the early, I think it was cat visual cortex, right? But even though they're kind of biologically inspired, right, they're not really very biological, okay? Artificial neural networks like we've been building aren't connected, like they're not structured like real neurons, and they don't act like real neurons. Spiking neural networks are very different from the kinds of models that we've been using, and they work a little more like an actual neuron, and they at least can be structured more like real neurons are. And what I mean there is connection pattern, right? Large networks of spiking neurons can be connected together in patterns like how human or rat, biological neurons are connected. All right. And I guess it should be mentioned that we're still not doing neuroscience, right? Just to go ahead and be clear, right? We're still ripping off neuroscience and not actually being neuroscientists, right? Because our models are still very much more simplified and non-biological and whatever works than like neuroscience is, right? We're still not biophysical. We're just getting a little bit closer, right? We're mimicking a little better. So why SNNs? Putting aside any kind of philosophical reason we might care about spiking neural networks, one powerful, compelling factor is that they are very efficient in terms of power, basically. So the human brain runs on very little power. I think it's single-digit watts, but I'm not going to swear to that. And it performs a lot of computation, right? And part of the reason for that is that biological neurons, right, spiking neurons, only, with like a little asterisk at only, perform computation when they are receiving and integrating and emitting spikes, okay? And the spiking activity in a real brain is very sparse, which basically means most of the time neurons aren't emitting or receiving spikes, right? So most of the time the brain isn't spending power processing neurons that don't need to be doing something, right? And because of that, it can perform very sophisticated tasks with very little energy. And that property can carry over to the kind of synthetic spiking networks that we build if we use an event-based architecture and develop it very conscientiously, right? We can design our spiking neural networks so that our spiking neurons are only being evaluated and consuming power when they are emitting or receiving spikes, right? Another is that they're innately time aware, right? So we recently talked about recurrent neural networks, and recurrent neural networks are an extension of artificial neural networks, right? To have a history and thus be able to be run in time. Spiking neural networks kind of don't require any adaptation. They're already defined in terms of their time dynamics, right? So we already define spiking neural networks in terms of how they change in time, which means they are just sort of innately time-aware things. Another interesting thing is neuromorphic hardware. So neuromorphic hardware is an area of research, good lord, that is really heating up lately, and what it basically is people making hardware that is very specifically designed to support connectionless networks very efficiently. That is designed for neural networks, right? So I forget the time frame. I think 5 or 10 years ago, work started on the memristor, which was a little superconducting element, or superconducting, good lord, which was a semiconducting element whose resistance could be varied, right? And what it basically could be used to do is build a lot of networks of these things that could very efficiently propagate and could very efficiently do the kind of math that we need to do for neural networks, right? That could very efficiently represent one element connected to other elements and could very rapidly and efficiently compute this element's, whatever value times some weight stored in the memristor and then update it. So when these get perfected, they enable us to potentially evaluate even very large neural networks for very low power consumption, right? And spiking neural networks may map very well to memristors. So